Right, I kind of miscalculated how long this is going to take, so I'm going to have to be quick, fast through it, because otherwise I don't fit it in. Hi, my name is Melanie. I do embedded software as a living. I do a bit of hardware as well, although that's not my background, but it's what I started off with. I went from electronics into computing as a hobby. And this is basically going to be from the very, very basic. So if anybody of you are thinking about how to make an next space rocket or something like that, then it's probably a bit too low level for you. But this is basically for people who know virtually nothing up to some basic interfacing. So we'll start off with basic discrete components, GPIOs, shift registers, SPI, I2C. If you don't know what any of the later models mean now, you will do later. So let's go to the basic symbols. What's current? Flow of charge. By convention, it goes from positive to negative. It actually goes the other way around. And measuring amps after this dude, who was a physicist mathematician. They were all physicist mathematicians. Voltage is basically potential energy. It drives the charge, makes the current flow. Batteries store potential energy, named after Volta, who actually invented the first multi-cell battery. He was a mate of Galvani, and Galvani, if you don't know, was the guy who used to electrocute frogs' legs to make them twitch. We also refer to currents and sinks, so the talk does include the kitchen sink. So we have current sources and current sinks, which is basically the positive and the negative. So resistance restricts the flow of current. In a crude analogy, it's a squash pipe. Also known as impedance in AC circuits. Resistors are things that create resistance. Measured in ohms after a guy called Ohm, and he came up with that law, which is that the voltage is directly proportional to the current, and the factor that combines the two is the resistance of the conductor that the current is flowing through. Another one, capacitance. I don't have my clock up. Capacitance is a thing that stores charge. That's a symbol. At a simple level, it is basically two metal plates with wires connected to it. When you first apply a DC current, there will be a bit of current flow and then it will stop, but AC current will flow through it. Measured in farads after Michael Faraday. 1 farad is a very big unit. If you look at a kind of a 1 farad capacitor, they're about that big by about that size. So you're typically talking microfarads or nanofarads in components. Use a very current over time of voltage. We use it for filtering, so you quite often see every little integrated circuit will have a small capacitor next to it to help smooth out the power supply to that chip. This next slide will look quite over the top, but the basics, don't worry about all the numbers. The basic thing is this shape. So you basically connect the current there, and the current goes, and eventually goes to nothing over an infinite amount of time. But that curve is determinate. So you can use a capacitor to time things. If you use a capacitor and a resistor, you've got a timing circuit. Just for completeness, I include inductance, which is the effect of the current flow through a wire will create a magnetic field, which in itself affects how the current flows through the wire. There's all sorts of magic to do with RF circuits and inductance and things like that, and I'm not going to bother to talk about it. But it's there to do the kind of the trilogy of resistors, capacitors, and inductors. And I talked about impedance early on. It's another name for resistance. It's just that when you have an AC circuit through things with capacitors and inductors in, you get a level of resistance because of the way the circuit varies and the frequencies. So, the only two bits of physics in the talk is this guy, Kirchoff, and he has two laws. And you can remember, and it's basically all current going into that point added together is the same as all current coming out of that point. So it balances. And he did another one called, which is the voltage law or the loop law, or which is that if we got that as a battery, that voltage plus that voltage plus that voltage plus that voltage comes to zero, because in some cases it's going backwards, so it's going to be negative. And given those two, we can work some things out. You want to use a resistor and you haven't got a resistor in your box of the right value, you can use two resistors. If you put them together in series, you just add them. And there. And that came from just using Kirchoff. So you know the voltage across it in total is 5 volts. You know the current's the same through both of them. You can add them. If you do them side by side, you come up with that one down there in parallel. The other useful thing about this one is this is something called a potential divider. It basically means if that's 5 volts and say this one is 2,000 ohms and that's 3,000 ohms, that will be 3 volts. Because you add the two and then use the bottom one. So these slides will be online later, so you can kind of get it in your head and then pull them down and go through them again. But potential dividers are useful. They're a crude way of converting from 5 volts to 3.3 volts if you need to in circuits. Diode, valve, lets current go one way. Basically, LED is a diode that lights up. Put the current one way in, lights up, put the current in the other way around, it doesn't do anything. It's still a diode. If you put a voltmeter across there, you will see that there is a voltage drop across the diode. It's called the forward voltage. And in LEDs, that tends to be determined by the colour, because you've got different elements in the LED that create the colour. Max current is about 20 milliamps. You can find these, basically go to RS or Farnell's and look at your 5mm red LED and it will list it. And why do you need these? Because you can't just wire an LED up to a battery and have it light up. You need to put an LED in there, a resistor in there to reduce the current. Where do those numbers come from? So you look at the circuits on the web and it says use a 150 ohm resistor or a 300 ohm resistor or wherever. Where do you get it from? We know the forward voltage across the red LED is 2 volts. We know it's 20 milliamps. We can do a bit of maths and we come up with 150 ohms for the resistor. So if we doubled the voltage, we could change that to, that would become 8, and so that number would go up to whatever it is, I can't do it in my head. Final thing, transistor, current amplifier. You can use it as a switch, which is probably what you were doing interfacing. I'm not going to go into lecturing about building Class A amps or anything like that. But so basically we're interested in small transistors that you can use as a switch. So that if you've got a GPIO pin and you want to control something that uses more current than the pin can support, you can use a transistor, and I'll show you in a bit later. So, now I've whizzed through that, I can slow down a bit because I can now fit the rest in. On to actual interfacing. So that's what you got on a Raspberry Pi, a bunch of pins. And on there you have power 5 volt and power 3 volt, 3.3 volt, ground, which is the other side of the power supply, bunch of things called GPIOs. Some other things which have things in brackets like MISO and MOSI and S-clock and SDA and so on. And they're basically an SPI bus, an I2C bus, a serial port, and general purpose I/O pins. So what are general purpose I/O pins? 1 bit input or output. They can be high, which is usually at your power level, so that would be 5 volts or 3.3 volts in the case of a Raspberry Pi. Older Arduinos, it would be 5 volts. Low, ground, 0 volts. Or what's known as high impedance, which is basically off. Effectively, it has a resistance which is like something like 10 megaohms, and if you look at that, that has a minute current flowing through it, so it is near enough effectively just disconnected. GPIO pins. So, we can stick a resistor and an LED between the power supply and the pin, and when we put the pin low, so it's ground, the current will flow from the 5 volts through the pin to ground, and the LED will light up. So actually that LED will be going on and off with opposite logic to the pin. Or we can set the pin as the input and connect a switch, and normally it will be connected to 5 volts through that resistor, and then if we connect the switch up, it's now grounded. Now I've got 2 resistors in here. You can leave this one out, but if you leave this one out and you get the pin, and you program your pin as an output rather than input, when you press the button, that's a direct short. Lots of current, and it's a bit bad when you've just blown the pin on your Raspberry Pi. The Pi also has that resistor built in, so you don't have to worry about it. The only thing is, if you remember that potential divider circuit we had earlier on, that's a potential divider. And if that voltage is too low, it won't be enough for the Pi to detect it as being on or off. So you have to make sure you get your ratios right. Now, I could give you a bunch of numbers, but the best thing to do is just to kind of Google these kinds of circuits, and somebody already have worked out the numbers for you. But if I remember right, the Pi one's about 1.8 kiloohms, so this is actually going to be quite small for it to work right, which then makes you wonder whether it's worth it at all, because the current will still be too high. So what I actually do, I don't use the pins directly, I use an I/O expander on my Pi, so that all I do is blow up a 2-quid chip rather than the Pi. Talked about current being not enough, 8 milliamps for a Raspberry Pi pin if you've got all the pins being used. So sometimes you want to boost them up. That's where we can use our transistor. So this is a typical transistor as a switch circuit. Again, that resistor is not needed. It's typically kind of advisable to be 10 times this one. You can leave it off. That actually comes out, you have to do a bit of maths to do it, but if you go to people like Matt over there, he's got single transistors in there where he's already selected the resistors to go with them to do this sort of thing. So you'll get that transistor and you'll get that resistor together. But then you just hook up the LED and the other one as normal, and you can have a nice, great big, enormous bright LED that uses half of 500 milliamps, and you're not going to blow your Pi up. Voltage levels. In the old days, it was all 5 volts. Then, because you could switch lower voltages quicker, because electrons take time to move, they keep bringing the voltages down and down and down again. Typically, the sort of electronics we use, it's 5 or 3.3 volts. connect 5 volts to a 3.3 volt thing, normally it'll make it go pop. There are devices that are called 5 volts tolerant, but you have to know they are, and a Pi isn't one of them. So don't connect 5 volts direct to a GPIO pin. On a Pi, you'll pop the pin. But I showed you earlier on a potential divider. So if you know the signal's going to be quite slow, it's kind of you pressing a switch or doing something like that. Use a couple of resistors, 5 volts in, 3.3 volts out, fine, you can connect that to the Pi. With an output, the problem is that the old devices which run off 5 volts, 3.3 volts isn't enough to make them switch. So you need to have a higher voltage than that, so you need to boost it up. There are a whole package, a bunch of different chips called TTL chips, transistor logic, and they're basic logic gates. And every now and then they bring out new versions of the same, effectively the same packages using new technology. And the letters between them, they're all originally numbered like 7400, 7420 and so on. And gradually over the years, they've got more and more letters stuffed between the 74 and the digits afterwards. And so the current ones, 74HCT00, for example, is one of the numbers. You'll need more background about it, but basically you can power them off of 5 volts and you can switch them with 3.3 volts, and the output will be at the 5 volt level, so you can then plug that into the thing that won't work with 3.3 volts. However, all the kind of Adafruits and cool components and whatever all have little level shifter boards these days anyway, which will take a bunch of signals and convert between 3.3 and 5 and vice versa. So that's the nicest way of doing it, using that. So if you've gone and got a module which is 3.3 volts and you want to use it on a 5 volt Arduino, get one of those and vice versa. So we've done a bit of electronics. We need to switch them. Now I've gone for Linux, and I've gone for basic low-level Linux because I started looking at what was available for Python, and there are several solutions for Python for this, but it seems like several people have kind of reinvented the wheel a few times, and they don't all use exactly the same syntax, and they don't all use exactly the same classes, and so it's simpler to work with that. So you need to turn on what user space GPIOs in your kernel. Now, the modern Pi distributions have it enabled, so we don't need to worry about it. But if you need to do, that's your kernel config. That's where you're checking your kernel config. You need this. This is useful because this enables some debugging utility stuff that you can find out when you actually do your GPIO stuff and it doesn't work and your LED doesn't go on. You can see that whether somebody else is already using the same pin or whether actually you really have used the pin you thought you were going to use and so on. So you need that. That's nice to have, and if you have that, you can use these two lines to see what the current state of GPIOs are using a debug interface. But basically, oh, come on, slow there. From a bash command line, these are what we've got. You can, so let's come around this side so I can reach. So that's your GPIO number. So if you go back to our diagram way back here, we got a number there, 23. If you wanted to use that pin, you put in 23 there, and that basically says we want to use GPIO pin 23. We're going to switch the LED, set it to output. Once you've done that, this subdirectory appears with GPIO, and that number there is the number that you stuck in there. And then you either echo 1 or 0 to turn it on or off. Alternatively, we could set that to in, and we can cap its value, and if it's high, it will come back as 1, and if it's low, it'll come back as 0. And you can do all that in bash, in the command line, and it just works.
Just a quick, when you say you set it high or low, those are both low impedance ones. Is there a way to set the high impedance disconnected state?
You unexport it.
Okay. Yeah, the obvious way, thank you.
Yes, I forgot to put this line in. When you're done with it, you'll want to unexport it. There's an unexport as well. Should have put it in there. Like in my slides. Interrupts. Well, you can write some code that keep looking at all the pins we're interested in, keep going around in a loop, saying if that something happened on that, something happened on that, something happened on that. Not very useful, uses lots of power, uses all your CPU, don't want to do it. What you can do is you can basically say, turn on the interrupts, which basically means if there's a change in the state of the pin, you kind of go to the process of I want you to do something. So that's what an interrupt is. Two types of interrupts you tend to find is level or state triggered, which basically means the pin is low so the interrupt goes off. And the interrupt might keep going off while it's low, or while it's high the interrupt goes off. Or edge triggered, which means it will only happen once as it goes from high to low or low to high, and then once it's happened, that's it. So if you don't catch that one, you've missed it. And that will basically tell the processor, so you might want to use this for a push button if you want a button to do something. So you actually, when the button presses, the signal changes and it signals the processor. If we go back to this, I'm missing a slide. You could set this, I'm missing a slide, it was when I trimmed them down last night. You could set this to be interrupt, and then when you, at the moment you see, when you cap that, it immediately reads the pin and comes back and prints the value on the screen. If you set that to interrupt, and you cap that, it'll just sit there, doing nothing. And then when you press your button, that will return and tell you what the value is. Now, because this is all standard Linux file stuff, it means that if you're using something like C or Python, you can do asynchronous I/O to check when things have happened. But I didn't want to go into too much programming, so I've just stuck with this. So if you were doing it in C, you could do a select or a poll on this file, and that would go off when the signal changes. Right. So if we go back to our, I must be better. Right. Come on. We haven't got that many GPIOs. We may want to use a lot more. So what we can use is something called a shift register. And it looks horrendously complicated, but basically, if you set, you've got two inputs and outputs, and this can keep going. There's only 4 there, but there's kind of in a lot of chips, it goes 8 or whatever. So in this case, you put, if you set that high, and then you pulse that pin, that will go high. If you pulse it again, the high moves to that one. If you pulse it again, the high moves to that one, and so on, and it shifts down there. So what you can actually do is you can, by setting the value of that and pulsing that, you can set out more than several outputs from just 2 pins. I know our shift registers work the other way around, but we'll just talk about that. So we can drive them just from 2 pins. So that isn't any particular language. It's using C-ish syntax in a way that a lot of people might understand, so whether they've done JavaScript or Java or whatever. But that's basically how you do it. So we've got a byte with a value in, a byte, and each bit in that is maybe the value and output of our shift register. We just work through each one, and so we take the first bit, is it high or low, set the output, set the data pin to high or low, pulse the clock, it moves once into the shift register. We then move our byte, so we've now got looking at the next bit in our byte. And we go around again and set it, and gradually at the end of that we go around 8 times. So that's moved out 8 times, and so if you imagine that's there as well, you'll have 8 output pins set to the value of the bits in your byte, just using 2 input pins. So those could be 8 LEDs, and you can set the value of 8 LEDs just from 2 pins. And this is a off-the-shelf shift register chip. So going back to our previous diagram, we have a couple of extra pins here which we won't get worried about for a moment. So we've got our data, pin 14, data and clock from that diagram. Now, this has also got a thing called a latch in it, which basically says, remember what state I've set you to. So we would do our 8 pins, and then we toggle the latch pin, which is pin 12, and then the 8 outputs are just set to whatever we set it to. And we've expanded our number of output pins from 3 to 8. And you could daisy chain them. So you could make it 16 and so on. Now that's still a bit low level. So people basically took the shift register idea and came up with what's called serial peripheral interface. Okay, we have a clock. We have what's known as MOSI, which is just basically the pin out. We have a pin in, so we can read from our device. And we have a select, because we have multiple more than connected. So this will be our Raspberry Pi or our Arduino. We've got our clock, data out, data in, and then that one selects this one. That one selects this one, and that one selects this one. So if we selected this one, these two will ignore the signals. But again, it is just putting data on the output pin and pulsing the clock. In fact, there's a picture. So, pulse the clock, and the data goes out, and the read data comes in. For whatever reason, it's always the high bit first. And that's our select line. So that's the one that shows which device we were writing to. Slightly annoyingly, when I came up with this, now we could decide which way the clock should be and when to actually, the hardware should read the levels. So there are 4 different ways of doing it. But I've really only ever seen these ones. There are other ones, but I've mostly seen mode 0 in the chips I've played with. But as before, you could drive it from GPIO pins. And that, if you look at it, isn't that different from the earlier pseudocode. If we go back a bit, we set the clock to low, setting the output pin depending on our byte, we're pulsing our clock's pin. But in this case, because we got an out byte and an in byte, we just got a little bit more code. So we pulse that, we set our data pin, pulse our clock pin, set our data pin, pulse our clock pin, set our data pin, pulse our clock pin, and gradually it shifts out. It's a lot easier in Linux. Okay, C, but if you go on to say like the Adafruit site and you Google Raspberry Pi, SPI, there's a Python extension which is very easy to use to drive these. But we just open our SPI device, master. The .0 is the actual slave device. So .0 will be that one. .1, .2. And then we write the data we want to write, or we read the data we want to read. Unfortunately, if you want to do it simultaneously, you have to start using some low-level ioctal stuff in C. But that's the header and the documentation's in the kernel source. But what uses SPI? One of the standard ones, an SD card uses SPI at its legacy level. So you actually need very few components for like an Arduino to use an SD card. Maybe, again, you're down to the basic issue is it uses 3.3 volts and it's not 3 volt and it's not 5 volt tolerant. So if you've got a 3.3 volt Arduino, just connect up the chip select, the MOSI, the MISO and the power, and that's it, it will just work. If you've got a 5 volt one, use a couple of resistors in there to bring the voltage down. Right, we're on the right home run now. I2C, I called it Next Gen SPI. They decided that 4 connectors was still too much, and we could go to 2, where you basically have a clock line and a data line, and the data is used for both input and output. So how do you pick what chip you're writing to? You actually now send an address before you send the data. You can do it from GPIOs. In fact, last year I was working with a colleague on a project where he did write the whole I2C stuff using, in low level, just using a bunch of GPIOs. It's not advisable, it's too much hard work. And most chips, most microprocessors have, microcontrollers have an I2C bus built in. So I2C, literally, you've got your microcontroller and then you just connect the SDA and the SCL from each of the chips you want to drive together. Slightly interesting thing is, you don't really need to worry about it, but none of these actually ever set the output high. They only set, they're either high impedance or they set it low. And these go high because there are typically 2 resistors connected to the supply line. On the BeagleBone you need the resistors, on the Pi you don't, because they're already on the Pi board. There's all sorts of magic. For example, what happens if this is writing to that one and then that one's trying to send data to that one, and there's stuff called clicking detection and so on. It's all done in the magic of the bits in the I2C controller and the microcontroller. I don't worry about it. There's an I2C tools package for Linux, which allows you from user space to scan your I2C bus and see if things answer, which is interesting to do, because if you do it on a Pi, you'll get the bits that are already I2C on the Pi bus to answer. And you can set and get data from it. Or you can do it from Linux. Again, that's C, but there are Python extensions to do it. Again, you open up the I2C bus. This time, we basically need to tell it the chip address. So every chip has its own address value. We need to tell it the chip address. Also, most chips tend to have multiple registers inside the chips that control various bits of that chip. So you'll need to say which register you want to write to or read from before you actually send the value you want to write or read to it. So in our one, we've got a byte value that we're sending to some register. If we want to read from it, we have to write the register value we want to read from out, and then we read back the value for that register. Useful I2C chip. Gives you 8 GPIO lines off of an I2C bus. As I said earlier, you can blow up GPIO pins on your Pi, short them, or you use the wrong voltage or stuff like that. I just use one of them hanging off the I2C bus on the Pi, and then I put everything on those. They're about £1.50. If I blow it up, it goes in the bin, I get another one. We have a few lines. We've got the clock and the data. These 3 pins allow you to change the address of the chip, because if it was just hard-coded, you could only have one of these on your I2C bus. But if you want more than one, you want to change the address of the chip. So you can basically connect these to 5 volts or ground, and it's a binary value, and you set them to, and it will change the address of that chip, so you can have multiple ones on the same I2C bus. SPI and I2C do not do interrupts. So you will still need an interrupt connection if you want to use interrupts. Typically what you do is you connect that straight to a GPIO of some kind and enable the interrupt on that GPIO. But it's optional. If you're only using it for output, you're only going to poll, you don't need to connect it. And there's a reset line which just resets the chip. So if it all goes horribly wrong, if you want a nice robust design, you connect that to the GPIO line and you can toggle it, and your port expander will reset. The 8 on the end means 8 GPIOs input outputs. Not surprisingly, there's a 23A16, which has 16 of them. Another one you might be interested in is an analog to digital converter. Another I2C device. Again, got address lines. It measures the voltage difference between 2 pins. So you want to look at a variable voltage on your Pi, connect one of those to the I2C bus on your Pi and read it. And that is it. I will have my slides up there. Are there any questions? And I know it was a bit verbal diarrhea, but
One thing?
yes?
Why is clock SCK? Serial.
lost everybody earlier on an old punch drunk call. Yeah.
I have another stupid question. Back on serial I/O.
Yeah.
Okay, why is Mosey connected to Mosey and not Mosey connected to the output?
To annoy engineers who build a PCB and then find it doesn't work and find that they've actually wired the two up the wrong way around. It's because it's called master out, slave in. So even if you're on the slave, it's still the master out and it's still the slave in.
Yes.
But that is one of the common bugs that you find in the hardware that people have gone and swapped them.
That's a mystery the universe solved for me. Thank you very much.
I've just got a question about the measuring analog values. So it says it measures the voltage difference across the two values. So do you actually get say an 8-bit value coming out of that when you read and shift them all in?
Yeah.
Right, okay. So rather than 8 individual bits, you're getting an 8-bit value across the represents voltage difference.
So divided by 8. There's going to be limits in there. You have to look at your spec. You can't go connect one to 5 million volts and the other
Of
to.
course, yeah.
But
yeah, it's all relative and it's divided.
it's relative and it's just and you just read it and well there are 12-bit ones, there are 16-bit ones, so.
Sure, yeah. Oh yeah, of course.
But you'll just basically you'll go through your I2C. You'll use your I2C bus, read from a register. What I didn't go into there is the I2C protocol actually allows you to read from multiple registers consecutively. So if you go to register 10 and read 2 bytes, it'll read from 10, or the byte from 10 and then the byte from 11. So you might find for like a 16-bit analog to do the convert, it's actually a 16-bit register. So you say, I'm going to read from register 10, but you actually read a couple of bytes, and it reads 10 and 11, they give you the 2 parts for the 16-bit value.
Thank you.
I was just going to ask about the port expander, because you talked about using Linux to talk to the GPIO pins, and then you said, oh, well, it's safer if you use this port expander that uses I2C. But I would think you can't just talk to that directly through the GPIO and Linux anymore.
No, you can't. You have to do a little bit more software. But as I said, there are, if you're using Python, say, there is easy to use Python extensions out there. And you have to do a little bit more work. So, for example, you actually have to write to a register of that chip to say which pins are outputs and which pins are inputs. Read from another register to read their values. So there's a little bit more work, but it depends on how confident you are with what you're wiring up.
Yeah.
Anything else? Okay, thank you very much.